channel. Today we will solve the combination sum 4 problem. After doing this combination sum 4, I will explain you a variant of this problem which is a slightly modified version. So first I will explain you the solution, then we will write the C++ as well as the Python code for this problem. So let's first understand what is the problem statement. So it says that given an array of distinct integer nums and a target integer target, return the number of possible combinations that add up to target. The test cases are generated so that the answer can fit in a 32-bit integer. So it means that we have to return an int variable, right? Uh, so integer value. So that's why we can see that here the return type is integer. So let's understand the example one. So nums is equal to 1 to 3. So it is an array of distinct integers. So elements cannot repeat in this array, and the target integer is 4. Return the number of possible combinations that add up to the target. So from this nums array, we have to find the number of different combinations of numbers whose sum is 4. So the first possible combination is 1 1 1 1. So we can take any element more than one times, right? One or zero or more times basically. So here we have taken one four times. So 1 plus 1 plus 1 plus 1 equal to 4. In the second combination, we have taken 1 two times and 2 one time. So 1 plus 1 plus 2 is again 4. And similarly 1 to 1, 1 3, 2 1 1. So here what you can see is that 1 1 2, 1 2 1 and 2 1 1 basically the same elements have been taken, but the order is different here. So here 2 is in the end, here 2 is in the middle, and here 2 is in the beginning, right? And similarly for 1 3 here and 3 1s. So basically the numbers are just swapped, but the elements taken are same. So and what is written here is note that different sequences are counted as different combinations. So yeah, so order can be different and they will be counted as different combinations, right? Let's take another example. Nums is equal to 9, target equal to 3. So here, um, uh, number of possible combinations is 0 because there is no such combination whose target is 3, right? What we can take out of this array? Just the number 9. So even if we take it once, even if we take this number 9 once, its sum will not be 3 ever, right? Because 9 is greater than 3. So that's why the number of possible combinations is 0. So this is the problem. Now let's try to uh, come up with a solution for this. So what we know here is that we have to iterate through the nums array, and at any point of time, I can take a number in my combination, or I cannot. I may not take it in my combination, right? So there are two possibilities. But after suppose here, if we go, if we take this example, I'll just open an Evernote pad. Yeah. So the given example is we have one, sorry, we have one, we have two, we have three, right? This is the array which is given to us, right? And the target is 4, right? So now suppose if I take one in my combination, if I can include one in my combination, right? So what my combination will become? It will, sorry, our target is 4, right? Yeah. Now I take, uh, say, 1 in my combination. Then my combination is currently 1, and my current sum is what? 1. Uh, Now I've taken this. Now I have the option to again take this or move on. Suppose I move to the next number, I will take 2, right? My sum will become what? 2 plus 1, 3. Now I have the option to again come back and take this one, right? So basically, It's not that I have to mandatorily move forward. I can come backwards also, right? After moving to 2, after including 2 in my combination, I can go back to 1 again any number of times, right? So suppose I go back to 1, I include 1 in my combination and my sum becomes 4. So this is one of the combinations which we can count, right? Which we can count as a valid combination because its sum is 4. So basically what I want to make you understand here is at each in each iteration or in each function call, suppose we use a recursive function for our solution. So in each recursive function call, we can iterate through all the elements of the nums array from the beginning, from 0 to n minus 1, right? This is the nums array. Why? Why? Because even after we come back, if even after we come to 2, or suppose we come to 3, right? Suppose, let's take another example. In my combination, first I have the option to take 1 or exclude 1. So I'll just suppose I exclude it. I'll move to 2. I can either take 2 or exclude it. Suppose I exclude it. Now I can go to 3. Suppose I make a choice to include 3 in my combination. Now again I can go back from the beginning again. I can choose whether to take 1 or not. Suppose I take 1. So my target becomes sum becomes 4. So this is also a valid combination, right? Valid combination. So basically what I want to make you understand here is in each recursive function call, we can go through the entire nums array starting from 0th index to n minus 1 index. Why? Because because of this only clause that the different sequences are counted as different combinations. So suppose if we don't iterate from 0 to n minus 1, suppose if we just keep moving forward. Okay, just we will keep moving forward. Then what will happen once we reach 3? Suppose we exclude 1, we exclude 2, and we reach 3 and we included 3, right? So we cannot include 1 now, right? If we don't have the option to move back, we cannot include 1 here. So we will lose out this combination in our solution. So that's why in each recursive function call, we have to move from 0th index to n minus 1 index of the nums array. So this is the requirement. And when can we stop this recursive function call? Right? There are multiple conditions, right? When we can stop this recursive function call. One condition would be first condition would be what? When target becomes when the say the current sum or sum becomes target. Suppose here, yeah, we'll take this example. 1 plus we included 1, then we included 2, then again we included 1. Our sum became what? Sum became 4 here, which is equal to target. So we will stop this iteration, right? We can consider this combination as a valid combination, take into consideration its count, and just return. I mean, no need to further continue the recursive function, because if we further keep including elements in this combination, our sum will become greater than the target, which we don't want and which is of no use. So, but whenever sum becomes target, we'll just stop the recursion. Another would be like when sum becomes greater than target. This condition. In this condition, we will not count the combination as a valid one. We'll just return. And when sum is equal to target, when sum is equal to target, then we will consider that combination as valid one and we will return, right? Return. But when sum is greater than target, then we will not consider that combination as a valid one. Like for example, here we include say 1, then 2 in our combination. So, and then include 3 suppose. So 1 plus 2 is 3, 3 plus 3 is 6. So 6 is greater than 4, right? Which is our target. So in this case, we will not include this combination, will not consider it as a valid combination. We'll just return and stop the recursive function call. So I think these two conditions would suffice to stop the recursive function call. And so basically how our recursive function call would look like is, say it's a helper function, suppose. So here we will have what? Some target nums as parameter, like, and then if sum is greater than target, then just return, or return 0 basically, right? Return 0 because we are not considering this combination as a valid combination, so we'll not count it, right? If sum is equal to target, then do what? Return 1. Because why? Because we are considering it is a valid combination when sum is equal to target. Otherwise, what will you do? You loop through the for I equal to 0 to n minus 1. Um, Here we can have an int result is equal to 0, and the result will basically have the count, will store the count of, combinations basically. Result plus is equal to helper, we are iterating from I equal to 0 to n minus 1. So sum plus nums I comma target, and what is the other? Nums, right? So what we have done here is will iterate from I equal to 0 to to n minus 1 for nums array, right? And include the current element in the, add the current element in the sum, right? What we are doing here, right? And then again call the helper function. So it will be called again here. And if this sum, that is sum plus nums I, what will this sum will have then? Sum plus nums of I. If this sum is equal to target, then we'll just return 1. So initially suppose result is 0, and then from each iteration we'll see whether sum is equal to target or not. If it is equal to target, then it will keep returning 1, and the result count will be incremented, and in the end we will just return the result. This will be an int function basically. Return result. So this will be our recursive function. Now what we can see here is we are calling the helper function again for some value of, right, for some, right, for some value of, for different values of sum, right? Basically, what is changing here in this helper function? Which parameter is changing? Target is same, right? Target is always same, which is given in the question. And nums array is constant. It is also given in the question. So only thing which is changing is sum, because we are incrementing the sum every time, right? So there are cases where what can happen is we would already have an answer for suppose sum equal to x. We would already have an answer with us, so we need not call this helper function, right? We need not call this helper function. We can just, instead of calling the helper function for the value of x, we can store this answer in some vector, and just we will, instead of calling helper function again, we will just add that value into our result, right? So instead of this, we can have something like result plus equal to, say, dp of x. I'm just giving you an example. So basically what my intention here is that instead of doing just recursion, we can add memoization to it so that it will become a DP solution. Why do we need a DP solution? Because we have, there is a sub problem, and result we need, and we need not call the helper function again and again for the same value of x. Like for example, here sum is suppose say 3 now. So for helper 3 comma target comma nums. If we have already calculated this once, already we are done with the iteration, all the iterations for this, then no need to do it again, right? We will store the value of this and in a DP vector say, and we will use it as and when we encounter the sum equal to 3 value, right? So let's go back to our C++ solution. So what is given here is this function combination sum 4, the nums array and the target integer. So first we'll create a vector, wait, of target size -1, and we will return helper nums target dp and 0 sum. Let's create our helper function. In target vector and dp int sum. So if sum is greater than target, we'll return 0 because we'll not count this current combination as a valid one. If sum is equal to target, we'll return 1 because we'll consider this combination as a current combination as a valid and we'll count it, include its count. And then we have what? If dp sum is not equal to 0, return dp sum. So that's what I told, right? Is not equal to -1. Return dp sum or int result equal to 0 for int I equal to 0, I less than nums dot size I plus plus res result plus equal to helper nums target or dp vector and sum plus, here we will add the current element, nums element in our sum, and return dp sum is equal to result. Let's see if the solution is correct or not. So this is accepted. Let's submit this. Yeah, so this is accepted here. So now we can just briefly once more understand the solution. So here we have created a vector of int called dp, which is of size target. So it can have target, for example, if target is equal to 4, it will have it's of size 4, and each element is initialized with the value -1. So this is what this statement means. And then we are calling this helper function. We're passing the nums, the target and the dp vectors, and this is the sum, which is initially 0. Like when we do not include any element in our combination, the sum will be 0. So these are the four parameters, and the helper function has this four parameters here. And as we discussed, if sum is greater than target, will not include the current element, current combination will not consider the current combination as the valid one, and then will return 0. If sum is equal to target, then we will consider this as a the current combination as a valid one, and then we'll count it as will increment the count by 1. And if dp sum is not equal to -1, return dp sum. Otherwise, initialize a variable with 0, result variable with 0, iterate from I equal to 0 to nums dot size, and call the helper function. And just the only different thing which we are doing here is adding the current element to the value, to the sum value, and then return dp sum equal to result. So basically this vector here, we are first storing the result value in sum, and then returning it. So basically what we are using, what our intention is behind using this memoization or dp vector is that, like for example, suppose sum is currently say uh, 3, right? Say, say, we'll take this example. Target is equal to 4, right? So how many ways we can reach the, how many different combinations are there using which we can reach the target 4? How many different combinations are there? So let's understand it here. So we have to reach the target 4, right? So, and the nums vector is 1, 2, 3. This is our nums vector. Now, number of ways to reach target 4 is equal to number of ways to reach target 3 plus number of ways to reach target 2 plus number of ways to reach target 1. Why is this so? Let's understand it. Because for reaching target 4, suppose there are three different ways, say five different ways to reach target 3. Just assume that there are five different ways to reach target 3, right? Five different ways are there. So one way, two way, three way, fourth way, fifth way. So we will reach target 3. Now to reach target 4, what we need to do is we need to just add one element, just to add one element to this combination, right? And we will reach the target 4. Same is the case with, suppose there are three ways to reach target 2. And to reach target 4, what we'll need to do? We need to just add one element, right? We'll just add one element to reach to this, and we'll just add one element to this combination, and our target will become 4, right? Like for example, let's see how many ways we can achieve, will reach the target. So there for this nums array. So this is 1 comma 1, 1 comma 1, and 2, right? These are the two ways using which, or the two combinations whose sum is 2, right? This sum is 2, right? Sum is 2 of these two combinations. Now to reach the sum as 4, to make the sum 4, what we need to do? Just add one or more element to this, right? And to this also. So what we'll do, we'll just add what? 2 here, suppose. So our this will become 1 comma 1 comma 2, and this will become 2 comma 2. So we have added just one more element, which is this 2, to these combinations, and our target has become 4, right? So we do not have any option here. We can just have one, you can just add one number or one element to these combinations, right? So how many combinations we have here? Here also we have two combination. This one combination, the second combination. This is same as the number of combinations we had for reaching two, right? For reaching two, we had two combinations. For reaching four, we have again two combinations only, right? Right. Suppose for reaching three, how many combinations we have? 1 comma 1 comma 1. We'll directly take 3, and another option is 1 comma 2. So the sum is 3 for these three combinations. For reaching 4, what can we do? We can add one more element to this. So this will become 1 comma 1 comma 1 comma 1. We can add one more element to this. So this will become 3 comma 1. We can add one more element to this. So this will become 1 comma 2 comma 1. So again, three ways to make the sum as 3, and three ways to make the sum as 4. So basically, the number of ways to make the sum as 4 is equal to the number of ways to make the sum as 3. Similarly, here the number of ways to make the sum as 4 is equal to the number of ways to make the sum as 2. So that's why the number of ways or the number of combinations to reach the target, or to make the sum as same as the target, is equal to target n is basically equal to, from target I equal to 1 to I equal to n minus 1, and from I equal to 1 to n minus 1, target I summation. Okay, so for target 4 is equal to target 3 plus target 2 plus target 1. This is what it means, and that's why what we are doing here is, if like that is what we are doing here with the DP. So in DP, basically we are storing the these values: target 3, target 2, target 1. So whichever we encounter, we just store it in the DP vector, and we just use it. We just return DP sum, right? So for example, uh, suppose the sum is currently 3, right? And if we have stored it already, we'll just return it. Suppose sum is 2, we'll just return it with number of ways to. What does DP sum store? DP sum store the number of different combinations whose sum is 4. Not 4, sorry. DP sum stores the number of different combinations whose sum is equal to this sum. So that's how this DP is working here. So now I'll write the Python code also for this problem. So let's see. So we'll just have here dp minus 1 into target. This is our dp vector, and we'll pass nums target dp and sum def helper self target dp sum. So here basically sum will be 0 initially. If sum is greater than target, return 0. If sum is equal to target, return 1. If dp sum is not equal to minus 1, return dp sum for I in range 0 comma nums dots not len nums will have another integer result here res plus is equal to helper nums target helper nums target dp sum plus nums I, then we'll store dp sum is equal to res, then return or return, yeah. Let's run it and whether it is correct or not. Let's see. If okay, so runtime error because we don't have any int in Python. This is accepted, and let's run it and see whether it is correct or not. Yeah, that's correct. So this is the solution for combination sum 4. Now let's try to do a variant of this. Okay. Now let's try to do a variant of this problem. So suppose here the different sequences are not counted as different combinations. Then can we do? Suppose 1, 3 and 3, 1 are counted as they are not considered as different combinations. Then in that case, and one or another case would be like 1, 1, 2 and 1, 2, 1 and 2, 1, 1. 1, 1, 2, 1, 2, 1 and this 2, 1, 1. These three are considered as one combination or same combination because they are just different ordering is there, right? It's a different sequence, but suppose we consider this as just a single combination, same combination. Then what would be the answer? Let's understand it in Evernote. So the nums given to us is 1 comma 2 comma 3 and the target is 4. Okay, so if we can if different sequences are not considered as different combinations, then how many combinations can we have to reach the target 4? We can have 1 comma 1 comma 1 comma 1, 1 comma 1 comma 2, then 2 comma 2, and then 1 comma 3. These are the four combinations, right? So answer will be 4. Currently the answer is 7 here, right? Currently answer is 7 because we have 7 different combinations and different sequences are counted as different combinations. Otherwise, if different sequences are not counted as different combinations, then we'll have which thing? This 1 1 1 1 in our solution. This 1 1 2 will be there. This is the first combination, this is the second combination, and this is the third combination, and this is the fourth combination. So we'll have the answer will be 4 and only 4 valid combinations will be there. Now how can we achieve this and get a solution to find a solution to get this answer 4. So here the difference which we see from the previous solution is that like once we are at any particular element, say 1, we can include it any number of times in our combination and right. But once we move to the next element, say 2, we cannot jump back to 1. This is not allowed here, right? So if we are at 1, we can take 1 any number of times. We have taken it 4 times here. In this case, we have taken 1 2 times and then jumped to 2. Now here, suppose we excluded 1, we jumped back to 2. Now we jump to 2. Now we can include 2 as many times, or we can go to 3, right? We can either include 2 as many times as we want, or we can go to 3, but we cannot go back to 1. So this is not allowed here, right? But because if we can go back to 1 or go back to the previous index, then we will not get uh, solutions having where different sequences are counted as same combination, right? Because then in that case, if we come to 3 and we can again go back to 1, we will get 1 again 3 comma 1 also as a possible combination, right? But we don't want this, right? So that is why, like, once we are at any index, we can include that particular index or element at that index as many times as we want, or we can move to the next index. So this is what our solution should do. So here there will be slight change, minor change in the helper function which we wrote earlier. So we'll have our int result equal to 0 as we had, but after that we were running a for loop, right, from for or I equal to 0 to n minus 1, right? So this is not required here. Why? Because we do not want to again iterate from 0th index to n minus 1 index. So instead of this, what we will do is we have two options, either to include, keep including the current index, element. So what will happen? Our sum will become sum plus nums index, right? And we'll keep including this index. Again, we will be at the same index, right? Actually, we will have three options here, I think. One would be to include the current element and then be at the same index only, right? This is one option. Another option would be to include or add the element at current index and move to the next index, right? And the third would be don't include the current element, just move to the next element. So here we are not adding anything to our existing sum or the previous sum. So these are the three options which we have. Either include the current element and be at the current element only, so that in the next recursive call, function call, we can again include the current element, or just simply move to the next element. So this first case would be for our first this example 1111. So we are adding 1 to our current sum, and we are will be at the same index, right? So that again we can add 1, again we can add 1, again we are adding 1. This is sum plus nums index and index plus 1. Yeah. So it would be like this thing we can consider, right? Here we are including this sum in our this one in our sum, and then we move to the next element, which is 2, right? This is the example of the second option which we have. And the third is don't include the current element, just move to the next. So like for example this one. So here when we start from 1, we have not included it in our combination, we have just moved it to the next element, which is 2. So these are the three different options which we have. So say if, so what conditions will we have here? If sum is greater than target, then return 0, of course. If sum is equal to target, then return 1. If again dp sum is not equal to -1, return dp sum or int result is equal to what? Helper nums. So here we will have one more element called parameter called int index nums, then target, then dp, then sum plus nums index comma index, right, plus helper nums target dp sum plus nums index and then index plus 1, right? So here we are including the current element, then moving to the next index, then helper nums target dp sum index plus 1, right, and return dp sum is equal to result. Here we will have one more condition, like if index is greater than equal to nums dot size. So here we have to take care if the index is not going out of bounds, right? So this will be the condition for that. So if index is greater than equal to nums dot size, return 0. Okay. Nums target sum plus nums index comma index sum plus nums index comma index plus 1 sum comma index plus 1. Right. Let's run it and see what is the answer we are getting. Okay, here it is required. So we'll basically start with zeroth index. So I'm passing here 0. Yeah, let's see what is the answer we are getting. Output is 52. Okay, let's ignore the DP thing as of now. We'll just do a plain recursion here and let's see what is the answer. 12. Hmm. If sum is greater than target, return 0. If sum is equal to target, return 1. If index is greater than equal to nums dot size, return 0. This is correct. This is correct. So here, instead of having a int function, let's try to have a void function, and we will have one int and count. This will be basically the count of the different combinations whose sum is equal to target. So in count, we'll just call this and then return count. We'll pass here count as well. So int and count. If sum is greater than target, just return. If sum is equal to target, then count plus plus and then return. If index is greater than equal to nums dot size, then return, and in each recursive function we have three options: return, sorry, call helper, nums target, sum plus nums index, comma index, be it the same one, right? And add the current element and move to the next element. Just move to the next element. Yeah, three options. Now we'll add just count also here. Count, count, nothing to return. Okay. Here also I need to add count. Why is the answer coming as 12? It should it should be 4, right? It should be 4. Vector int and nums int target, vector int and dp int sum int index int and count. So I've taken passing it by address. Count plus plus return 0. Okay. Okay. I think these two options should suffice. Yeah, output is 4 right now. So here basically what I've done is we have two options. Either, wait, I'll just have the DP based solution. I'm just undoing it so that we move to our initial solution. Yeah. So instead of having this, we'll have just two options. This is accepted. Obviously, it is not a correct. Again, I think I need to move to my previous approach. So instead of having a TP-based solution, let's have this return nothing to return actually. Here helper. Then I have here int count equal to 0. Return count and count, then add count in the parameters, run it. Hmm, it's a void function, so it should not return anything. Correct. Here also, it will just return. It will not return any integer since the helper is the void function as of now. There is some error. Invalid operands to binary. Okay, invalid operands. Okay. Nums are dp 0 0 index 0 0 count. Okay, we are adding here one. So we are adding two functions. So we have to just call it and Let's see what is the result now. Yeah, the output is 4, which is what we wanted, right? And let's see what is for case 2. For case 2, output is 0. That is as expected because here sum cannot be equal to target in any case. So yeah, so this is the a variant of the combination sum 4 problem, and the solution is basically you can either include an element and keep including it, or just move to the next element. So this is what we did here. Two options are there. Add it, like suppose we added here some 1, and we are at 1 only. We can keep adding it. Or suppose we are at 1, we added it. Again we are at 1, we added it. We are at the same element. Now we move to the next element. So these are the two options which we have. So hope you understand the question and the solution. Thank you for your time. Thank you.